Hello, my name is Bertie and I'm here to show you how to get into JavaScript and write a little bit of a game engine with the minimum amount of effort applied. This video is to serve as a introduction to WebGL for JavaScript users, but I also want to design it in such a way that if you're completely new to programming, then this is the quickest way you can start getting results without having to download too many additional tools and without any previous real experience. If you are coming from this fresh with no programming experience, a lot of these concepts might be intimidating, but at least you'll be able to get something running on yourself by copying this code, and you can see just a little bit of how it works, and maybe afterwards you can play around and get some of your own results. But first, let's do a quick overview for what WebGL actually is. Behold my diagram. WebGL is just OpenGL for the browser. There's a few terms you're going to hear. One of them is vertices. And what a vertice is, it's a point that has an X and a Y coordinate. And if you're working with 3D, it'll also have a Z coordinate. So that's just coordinates in space. Also, for our purposes, we'll also be using texture coordinates as well as positional coordinates. Texture coordinates will tell us what part of an image to sample. So the steps that OpenGL goes through is, first of all, we feed it some coordinates, these positional coordinates and these texture coordinates. They go into the vertex shader. And what the vertex shader does is changes the position of those depending on whatever vertex shader we've written. And what we get back out is a rasterized mesh, which is a fancy way of saying we get the actual pixel positions of all these coordinates. Once we have the pixel positions, we use our fragment shader. And what a fragment shader does is actually draws in the colored information. So we'll use our texture information to find which parts of our initial image to use, and then to draw those onto the screen. And then after it's done all of the different meshes we provided, it produces a final image in which we use to display on the screen. And everything that's happening on the WebGL layer is happening on your graphics card, so it's a lot faster than running it just natively in JavaScript. So what I'm going to do first is I'm going to create a new folder, and we're going to call it 2D engine. And when we're going to run this application here, again, if you're familiar with making websites and stuff, you may not need this step. HSF will serve files from your computer as if it's a website, and this will be necessary if you want to serve images and media files. HSF is probably the simplest way of getting this set up without having to mess around with Apache and other complicated software. So let's see, add folder from disk. And so we can see here, there's my new folder, 2D engine. Hit OK, we want to make it a real folder. And now if I go to this address that it provides at the top, we should see nothing. This folder is empty. But it means it's working, and that's the important thing. Always a terrifying moment whenever you're on video hooking up one of your own local files. You never know what embarrassing thing might pop up. Although what this does confirm to you is that I do have something to hide, and yes, I'm hiding it from you. Anyway, so let's get into this folder and we'll create a new file. And we'll call that file index.html. Yes. So now whenever I refresh this, it'll open up a blank page, which is my index.html. So let's get editing that. If you're completely new to HTML, every HTML document starts off with a doc type. This stuff's probably not that interesting to you. You're more interested in the programming for video games, in which case you can largely ignore this. This is just a very straightforward HTML document. So we have our head tags, which defines information about the file, and then you have a body tag, which defines the document text in general, which we're not going to need any of that. But just to show you that this is all working, what we're going to do is create a h1 hello world. Look at that, isn't that beautiful? Anyway, so we now know that the document's working, so let's just get started with a little bit of JavaScript. You want to import a JavaScript file, you write script.src equals, and the name of our JavaScript file is going to be js, which is going to be a subfolder, and we'll call it game.js. And that's it. Now we just need to create that file, oopsie, by opening up a new file, and we'll do an alert. This is JavaScript. We'll save that in a new subfolder. JS game.js. And there we go. Incidentally, I'm using Notepad++, but other text editors are available. Anyway, so there we go. This is JavaScript. So we now know that this JavaScript file is working. Just to get this out of the way, again, if you're not interested in HTML, this can largely be ignored. But what I'm going to do is I'm going to write a short little style guide for my web page. Since we don't have much style overall, I'm just going to put it in the documents header like this, rather than create a separate external style sheet for this. So what we're doing here is turning the margins to 0 and the padding to 0, which means everything will kind of sit against the edge. Then we're going to set up body. I'm going to set that to overflow hidden, which means anything outside the visible body will be hidden. Canvas, going to set that to background black. And that'll do. It'll do very little to the document, but gives us a start. Alright, so let's just pile on in. Class, game. This is going to be our game class. Save that. And we'll set up a little script here, which what it'll do is window.add event listener. And the event we're going to listen to is load. And the function that gets called afterwards we'll define here. I'm sure now we could like use like promises and such like that, but I'm just used to doing it this way, so I'm just going to stick with it. And just to make sure that this is running, would you test tisd in my case? Okay, it's running fine. And then after we do this, we want to do, let's see, once it's finished loading, we want to create a new instance of our game class that we just wrote. So window.game equals new game. And then once we want to call function loop. In addition to class, we also want to set up a loop function, and all this is going to be is function loop like this, which is going to look for window.game.update, which is going to run every frame, and then request animation frame loop. So it calls itself back again, effectively creating a loop. The request animation frame is a function that means that this this function here, loop, won't be called until the next frame is available. So just a way to stop it from running, you know, an infinite cascading loop in one frame. So we have our onload function, created a new instance of game, and then we have it called the loop function, which loops through the game. So we need to create that update function I just wrote there, and as well as a constructor. So we'll get the constructor out of the way. Nothing in it. And then we have update, another empty function. So whenever we run this, all's well and good. Now, new to JavaScript, new to programming. The reason why I recommend JavaScript is because JavaScript has quite a lot of powerful tools. And one of the ones you can do is if you're using Chrome like I am, you can just press F12, which will open up the WebKit debugging tools, which are these, which give you a great deal of power over the way things execute. You can run commands as it's running, that kind of stuff. So we can see, if I even type in here, window.game, we can see we've got our instance of game, and we can do more stuff to that later. Anyway, in the meantime, let's get stuck straight in. So what we need to do, first of all, is create a canvas. A canvas, if you're not familiar with HTML, is just a, how to describe it quickly, it's a element like that goes into your page that you can quickly make changes to without having to refresh the entire DOM, which makes it very efficient for games. You could potentially make a game using image tags and stuff moving across the screen, but it would be incredibly slow. So this gives us a bit more flexibility and a lot more speed. So we just do this document.createElementCanvas. Canvas. Make sure I've spelled it right. And we set it some sizes. Set canvas.element.width. We'll give it a default width of 800 pixels. And we'll do the same thing with the height of 600 pixels. Okay, that's good. So that's not enough though. What we need to do then is add it to the document itself. So we go document.body .append child, which will add an element to the body of the document. And then we go this dot canvas element. this here, this keyword, what this means is it references that this is a variable or an object or whatever that is a member of the game, the instantiated game class. That's all it means. If that's too confusing, don't worry about it. So now that we have that set up, we can see now that it has indeed added our canvas, which is 800 by 600 as we specified, and there it is, nice and black in our page, like my heart. Getting on with it, we need to now create a context. So we go this.gl, okay, will be our GL context, and we create that by going this.canvas element, so reference the canvas again, get context, and WebGL2. So that's like WebGL, but it's got a 2 on the end. It'll give us some extra features that I'm sure are important, but I'm not going to go into here. Okay, so now that we have our context, we want to add something else. We want to start loading in some sprites so we can draw them onto our window, and generally just getting things going here, get a little bit of rendering, a little bit of update so you can see some stuff going. Anyway, so to do that, we're going to do, every time we run a new frame, I want to do gl.viewport, which is going to tell OpenGL what size its drawing context is. So we're going to set it to 0, 0, so it starts at 0, 0, and then we're going to set this dot canvas element dot width, which specifies the width of the canvas and the height of the canvas. And then we want to set it to clear, so that way every new frame it'll have a blank canvas, the render, and won't try to draw over what's on the previous frame. And we wanted to use something called a color buffer bit. And so this update function, as you can see, gets run every time the loop updates. So if I run that, it'll do very little, but at least we can see no console errors. So it is compiling and running correctly. Next, we want to set it to this.gl. I want to set some sort of, we want to set it to enable, no, not enable plugins, enable, and then we do this.gl.blend. If none of this is particularly intuitive, which I know it isn't, just feel free to move on for now. The important thing is getting this set up so that way you can get some basic images that you've made displayed in your browser. And then whenever we finish, we want to set up a blend function first though. Blend function, and this tells OpenGL how we want alphas to blend. Well, how everything blends actually, how images draw on top of each other. So we're going to use alpha and this.gl 1 minus src alpha. And I think what that means, I might be wrong, feel free to correct me in the comments, is that what it does is it takes 1 minus whatever the alpha is, then draws the other one at whatever the alpha is on top of it, and so it creates a nice blend between the two different channels. Could be totally wrong, but I think that's generally the idea. You're specifying what the calculation is for how different colors overlay on top of each other. And then at the end, flush everything, get rid of it, put it in the toilet, and make sure everything runs okay. Ooh, we've got a first error here. src alpha. Why is it not like this? Oh, it's because I wrote context instead of GL. There we go. Grand. Alright, so what we've written here is effectively every frame, it runs this update function, but whenever you first create the game index, or the game object, what it does is it creates a canvas, sets the width and height of the canvas, creates a WebGL2 context, which is whatever we want to draw onto, and then it appends the actual canvas into the body of the document, which is what this black rectangle is. And then on the update function, all it's doing is setting the viewport, clearing whatever's already been drawn there, and then enabling drawing mode, which is blend, and then how it blends together, and such and such and such. Okay, so what we're going to need, the next big step, the next big frontier, is we're going to need to determine some shaders. And to give a quick overview of how OpenGL works, we need to first of all explain what shaders are. So what shaders are just like little programs which specify how inputted data, which is usually things like image data or triangle data for polygons and 3D objects and that sort of stuff, how that stuff is actually treated once it arrives inside your GPU. So we need to write a couple of shaders and specify how that stuff's going to be displayed. It might be a little complicated, but for the getting something, just today's objective is just to get something on screen. So we're not going to worry about shaders. Don't you worry your little head about that. So we're going to write our first shader here, and what it is the type, and we're going to make it a vertex. Make sure I spelled vertex right. Shader. And we're going to give it an ID and call it, I don't know, VS01 or something. And we close it like this. I'm going to do the same thing for what we call a fragment shader, and I'll tell you what each of those do in a second. So a vertex shader, whenever we tell the whenever we give OpenGL some information, it's usually in the form of vertices. And vertices are like points in 3D space or 2D space in our case. That have X, Y, and Z value, and then it takes this X, Y, and Z value, runs whatever I write in here on them, and then that's passed over to the fragment shader, which then draws the actual pixel information that that we've created using the vertex shader. It'll become more apparent as you use it, but that's just a brief overview. So what we need to first do is create attributes. This is going to be some information that we load into the vertex shader. So a position, it's going to be a 2D position for us, so it's vector 2. Attribute vec2, and we're going to do a text coordinates. This is going to be the UVs or texture positions of the object we're drawing. Again, this stuff will become more obvious the more we work with it. And one thing we're going to have to pass over is a varying. So we need to carry over a variable from our vertex shader over to our fragment shader, and we use this using a varying type variable. Then we need to create a void main. So this is the actual routine that gets run in the vertex shader. And we do simple GL position, which is the final position after the what is called rasterization. Whenever all the calculations are run on where the vertex should be on the screen, on the 2D screen that you're looking at. So we set that by just simply taking the input information, which for us is just going to be the original position, putting a couple of ones in it so it eventually forms a 4-dimensional number. It's not really important why it does that. It's more for when you're worried about like more high level stuff. I don't know what I'm writing here. And we want to set the text chord to just equal the same thing that we put in. Okay, so effectively all we're really doing with our vertex shader is taking the input information and pretty much putting it as output information. We're not doing any strange transformations or anything to it. We're just simply taking what we send in and then putting it back out again. So whenever it reaches our fragment shader, we pretty much have the same, as I said, the same input. So we set, first of all, our precision. It doesn't really matter what that is for the moment. Uniform sample 2D. So this is a variable type sample 2D, which is just a 2D texture. That's what we're gonna actually display on the screen. Then we're gonna call it uImage. The U underscore is a prefix just saying that it is a uniform type variable. And then we're going to take our varying from our vertex shader, which is a vec2, and I call it v underscore texture. So you can see this varying here, it's got a v underscore text coordinate. So it comes through in our fragment shader, and we can then use that to sample our image, and from that we can pull individual pixel information out of our 2D image. So GL frag color, the final color after everything else has been calculated. We use texture2D function, which is going to take in an image, our uImage, there it is, and also some 2D coordinates, and sample that pixel from the image and then put it into here. And that's pretty much all we really need for the shaders at the moment. This stuff, this is the real meat of image processing in OpenGL. But for the moment, we don't want to get too deep into it. It's just enough to know that there is a vertex shader and then there is a fragment shader. So we need to get these two shaders and create what is called a shader program. And to do that, we're going to write a new file. So, new file here, class. I'm going to call it class material. It helps if you use a lowercase c. So I'm going to save that. Oop. There we go. I'm going to call this material.js. And that's all there is at the moment. And in addition to importing our game script, like here, I'm going to get it to import material. So after everything we've written, everything still compiles and runs just fine. Alright, so what do we actually need? We need a constructor. For those less familiar with programming, constructor is what function is called whenever you create a new instance of this object. That probably means nothing if you have no experience with programming at all. But maybe just do a little search into like what object-oriented programming is all about. These are some fairly high-level concepts I'm discussing, so if you're not really familiar with them, that's alright. They'll become more apparent the more you do this stuff, but it's enough just to say at the moment what we're doing is writing the function that gets called when we create a new object of type material. So we want to save the GL that we pass in, which is going to be, that's going to be our WebGL context. So we're going to save that as a local variable inside the material itself. Then I put in these parameters here, VS and WS, and what they're going to be is, they're going to be the actual scripts themselves that we call. In fact, just to show you that working, I'm going to do console.log.vs and console.log.ws, and that's where we're going to start. This shouldn't do anything yet because I haven't set this up, but if I go back into my game function here, I want to create a new material. So var mat equals new material. Okay, but beyond that, I'm also going to have to load in the actual shader information that I wrote in my index file. And so to do that, I'm just going to go to document.getElementById, and I think I called it vs_01, which is my vertex shader. And then get the inner HTML. I'm going to call that vs. Okay. And do the same thing with fragment shader, fs. And get the inner HTML. What other information? So this.gl, like that, vs and fs. So now that I have that all written up, we should see an uncaught error. So what's happened here? Is it that it's failed to get this? Have I spelt it wrong? Oh, they're both called vs. There we go. That should do it. Okay, and there we can see the code that we wrote for our fragment and vertex shader being outputted there using the console.log. Okay, that's good. So, right, what we're going to do is go let vs shader equal, and we go this dot get shader, and then we put in vs, and then we put in the type, which is going to be gl dot vertex. This is a vertex shader, so like this, and we do the exact same only with a fragment shader, and we have to change this to fs, and this also becomes fs. Then we actually have to write the get shader function, which is going to look like this, and it's going to have, I don't know, we'll call this script, and we call this type like that. So right, let's get the, first of all, let gl equal this dot gl, and let's see, var output equals gl create shader of type, and the type, if it's a vertex shader, is going to be this, and the type, if it's a fragment shader, is going to be this. So, and then the script itself is there. All right, so we go gl dot shader source, and then we actually put in our output, and then we put in our script itself. Then from that we compile it. Compile shader as output. And then let's see, that should probably do it. Output, there we go. So returns output and then sets them as these functions. Okay, that seems to have worked just fine. In fact, let's have a little introduction into breakpoints. So let's just put a breakpoint there, and I can see that this is actually returning a WebGL shader, so I can see that those functions are at least returning something. However, it's important to put in some error checking here, because if I went in here and just like put in, I don't know, bums lol, and then ran the script, I don't get any errors, even though there's no way that could really reasonably compile, because it's absolute nonsense. And see, it looks like it's worked, but it hasn't. So we're going to put some error checking in just to make sure that like whatever shader language or shader code we give it actually makes sense. So we go if gl dot, let's see, get shader parameters. We put in our output, and then we go gl compile status. So has it compiled? And we're testing it like it's a falsy statement. So if it gets back nothing or 0 or some sort of status that doesn't make sense, it'll throw up an error. And then from there we can just do console.error, and I don't know, let's see, we'll do this. You go shader error. Ooh, that does not look good on this particular display, but I'm writing shader error. I hope you can see this. New line, and you know what, actually I'll just use the old method just because this looks so bad. So new line like this, plus gl get shader info log, and then output like that. Okay, and then we want it to return null. So if there is an error, it'll display an error message, and then we'll get a null effort or null thing back, so that way we won't get anything. So now we can see this is indeed error lol syntax error. So you can now see that we're getting a bit of an error output. So error on line 0, the word lol, syntax error. And if I get rid of that, and now we can actually see that there is a genuine error on line 0 of this one. Finding it might be a bit of a trick. Ah, there's my problem. It should say sampler 2D, not sample. And there we go. We seem to have compiled the shader successfully. So once we have these two shaders, and we want to test to see if they do work, so via shader and fs shader, so they both return something sensible. What we can do then is we can create a program. So we'll go this.program equals gl create program, and gl. So we need to attach our shaders to this new program we've created. This is our shader program I mentioned earlier. So this.program, and then our vs shader. And we do the exact same thing with the fs shader. And then we link the programs with a rather unintuitively named link program. And then let's just check and make sure that this is all above board by going gl get program parameter, this.program, and gl.link status. And we ain't talking no Zelda. So if that returns back a falsy result, then we can do console.error cannot load shader -- and then we put out a error message. Get program info log. This, oops, see daisy. This dot program, like that. Okay, that should do it. And then return null. And hopefully we don't have any issues. GL link program is not a function. Oh no, I put an E in. My silly UK English ways. There we go. Easily fixed. See, you're watching me do this live, so you're seeing me doing mistakes in real time. Alright, so assuming that all works, let's just get rid of the garbage. So GL, we don't need, now that we've created the program, we don't need those shaders attached, so it's good practice just to remove them. VS shader, like this. Exact same thing, the FS shader. So, oop, there's another typo. And then we need to delete the shaders. VS shader like this. GL, delete the other shader. FS shader. And yeah, I think that's pretty much it. So we've created our shader program, and just so to confirm that, I'm going to put a breakpoint here. And then if I refresh, you can see here that's created a WebGL program. So we now have a functional shader. So that's good news. Let's make it display something. By now you're probably starting to notice, we've been doing this for a little while, we've written out quite a lot, and we still haven't got a single thing displaying. In fact, all we have is a horrible black square. When do we start displaying images? Well, it's coming. I can promise you it is coming. But I guess this shader program, while providing, while constructing and error checking a shader for us, doesn't really have any rendering capabilities. So we're going to create a new object. We're going to call it class sprite. Now, if you're more familiar with the broader concepts of a 2D engine, the word sprite probably fills you with a little bit of pleasure, knowing that we're getting closer to actually representing something on screen. So what we're going to do is we're going to first of all write our constructor method. And constructor method, like our constructor method for material, will take in GL, but this time it's going to take in image URL and a vertex shader and a fragment shader. So it's much the same as this constructor, except for now we're going to take in an image URL as well. And to get started, let's just get an image into our project. So I'm going to create a new IMG folder for my images, and it doesn't really matter what I use, so I'm going to use, let's see, something kind of cute. Okay, I'm going to use this little fella carrying a bucket of sludge. You can see him there. Isn't he adorable? So this is called nult.png. We'll remember that later. It's in the subfolder .img. So within our sprite, we're going to save another copy of our GL like that, this.gl, so we can make references to it later. We're also going to have this.isLoaded, and by default it's going to be false. And we're going to use this to track the state of the image that we're actually loading into the sprite. So whenever we first load the image, obviously it needs time to read off the hard drive. There's going to be a slight delay between when we ask it to use the image and whenever it's finally loaded in. So we just put in this isLoaded to track that. And then we want to give it a material. So whenever we load in a new image, it's going to create a new material associated with that image. And so this is how we create a new material, GL, and then we pass in our vertex shader and a fragment shader. And this will run this constructor once this is created. So it gives us a material associated with the sprite. Then we're going to create this.image. Ooh, I can't type. Which is going to be a new image. I'm going to create this image and we're going to make it give it an src, and then we're going to make it whatever the image URL is. And we're going to go this.image.sprite equals this, which is going to be a reference to the actual sprite object itself. So if I ever reference this image again later, I know I can check sprite to see what sprite it's associated with. And then finally, this.image.onload is going to be an ominous function, which means whenever the image is actually loaded, it means it'll run this function. And right, we need some sort of setup function. So this inside of this onload function references the image itself. So the way I associate sprite with it, so this dot sprite. Now I could use promises and all the ES6 features to make this a little bit neater and everything else, but I'm just going to make this simple because I'm going to stick with what I know best and just run a setup function, which we're now going to write. So we have a blank function which will be our setup. If we go back to game, when we first created a new material, rather than creating a new material, we're going to create a new sprite, and we need to add in the name of that image file, which we put in img. Let's see, img, and the name is nult.ping. I'm assuming you're going to have your own image on your own hard drive, so whatever that image is, write it in here. And now let's give that a try. No errors, but we're still a long way from going from actually displaying an image on screen. So you can see here, yeah, we've actually got our little image in. There's our image.nult. There doesn't seem to be any problems with the network. You see that it is actually successfully loading in that image. So everything seems good to carry on for now. And assume we have a material. Yep, there it is, our material associated with the image. Okay, moving on. So this is going to get a bit more complicated here. I'm going to go with this.gl. So we're going to actually, once the file itself is loaded, we're going to have to do some do some work to it. An image object that HTML uses isn't appropriate for WebGL, so we're going to have to run a wee bit of a conversion to it. So first of all, we load and use our program. Whoops. Our program, and we're going to use this dot the associated material with a sprite and its associated program. So there we go. We're now using our material. Then let's see, what do? We create a new this.gl texture, a WebGL texture, or 3D or 2D sample texture, whatever you want to call it. We need to create a new one of those. So first of all, we create the memory allocation for it. Then we set some properties. GL, let's see, text parameter I. And we call GL texture 2D because that's what it is. GL, and then we want to give it the property texture. Let's make sure I'm spelling everything right. Wrap S. And so how does it wrap? And we tell it we want it to be merge repeat. And so this means that whenever we go outside the constraints of our image, it'll repeat, but it'll repeat in such a way that it's mirrored. And then we do this both with S and T. And just a quick check to make sure everything's running just fine. Ooh, it doesn't like some of this. What's gone wrong? It says no texture to bind. Oh, I forgot to bind the actual texture. So first of all, we've created our texture here with the create texture function. I know it's insane. But we do need to bind the texture using GL texture underscore 2D, which is what it is, and then the name of our texture itself, which is gl.txt, the one we just created. Now we've run that. There we go. Hunky dory. No errors. So we need to create a few more properties. This one will be its texture magnification filter. So this is the filter it'll run if the image is expanded beyond its native resolution, which is pretty much very common in any kind of 3D or 2D graphics processing. So we're going to set it to nearest, and nearest neighbor is a technique for sampling images that get bigger or smaller. What you're probably used to seeing is something called bilinear, which is when the image gets shrunk, the colors sort of blend together kind of nicely, sort of hiding the fact that it's made out of squares. But nearest neighbor doesn't do any of that. Instead, everything looks blockier and badly sampled, kind of chunky. It's really, this part here, whether you use nearest neighbor or bilinear or one of the other techniques, is kind of up to you and how you want your game to look. But since we're going for kind of a 2D platformer, I'm thinking something like pixel based, you know, where the actual pixels matter themselves, you want clarity. So nearest neighbor, while it can make things look kind of gross, is also can give you a lot of clarity, a lot of sharp edges. And so we're going to use nearest neighbor for now. But if it's not right for your project, look into it and see what other techniques might help. So, okay, texture, image, 2D. We're going to use this texture, image, 2D to actually assign our image that we loaded in through HTML to the texture within OpenGL. So we set it up to, so it's a texture 2D, and it's going to use RGBA, which is 4 channels, so it's a 32-bit image. GL unsigned, unisigned, unsigned byte, and then we're going to put in the image itself, like that. Okay, so that should hopefully put our image into the memory. GL texture 2D null. So we unbind our texture at the end. Okay, and let's see if this runs fine. No errors, so it looks good. But since we're doing a 2D engine, the only thing we really need to worry about and render on screen is typically just rectangles. Just varying sized rectangles will represent our 2D characters on a 2D plane. We don't have to worry about complicated 3D shapes or strange kind of animations that applied to like complicated meshes. We just need to really render a rectangle. So what we're going to do is we're going to create our geometry buffer. So I'm going to call it geobuff. I'm going to go gl.create buffer. So we just want to put in some very simple data for our first buffered array. Array buffer. We're specifying that it is an array buffer, and we need to specify which one we're talking about. So it's going to be our newly created geobuffer. So it's now assigned as a type of array buffer. Now we need to put in the data itself. And we do this by going GL array buffer. That's what it is. Oopsie doodle. Array buffer. And then we're going to have to create some data here. Let's just write placeholder for the moment. And we're going to set it to GL static draw. Okay, so this placeholder, this is going to actually be our coordinates for our rectangle that we're going to use to represent each individual sprite. So let's actually just write something that'll create that for us. So I'm going to create a little function down here. I'm going to call it something like create rect array. And it's just going to be a handy function. You know what? I'm going to keep everything nice and object oriented. So I'm going to make it a static function. Create object array of, and what we're going to do is go x equals 0, y equals 0, width equals 1, and height equals 1. So this is our default values we want for our newly created rectangle array. And what we're going to do is return, I'm going to return a new float 32 array, which is a special kind of object in JavaScript. JavaScript can create arrays natively. You know, I can do an array of integers like this, 4, 5, 9, 6, blah, blah, blah. But that also comes with like a little bit of extra baggage. You know, this buffer can shrink and grow, and you know, you can append stuff to it, and it doesn't necessarily have to just contain integers. So we use something that has a bit more of a strict type here, which is a float 32 array. It's I believe it's 32-bit precision, so it's a fairly big precision for a number. So, and what's going to go into this array is going to be our coordinates positions. So we need to create a rectangle. So what's a rectangle made out of? A rectangle is made out of, in our case, 2 triangles, and So one triangle has 3 points, so we're going to need 6 points to represent our whole triangle. We could start messing around with things like faces and stuff, but since literally all we're doing is using using 2 triangles to represent a square or a rectangle, we don't need to worry about things like faces and such. So to keep things simple, what way a triangle would be its x position would be at 0. So this would be its origin position at 0, 0. Then it would be 1, 0. So x and y of the second point, and the third point of the triangle shall be 0 and 1. Then we go on to the second triangle, so we're going to start with the last one left off, so 0, 1, and then we're going to go 1, 0, and then finally the top right corner, 1, 1. So I'll put a little illustration of what that means in the different points, and that means those points will be pushed into our vertex array here as a position, and then that'll eventually form triangles, which our fragment shader will then color in using our fragment shader's information here, which is just sampling something from an image using the coordinates that we supplied. But this is just going from 0, 4, so it means that every single shape will be the same, but we've got a few variables here to control that. So 0 will be x, whereas 1 will be x plus w, the width that we supply, and we do that all the way down this first column. So now it gives us a bit of control over the shape and starting position of our newly created rectangle. So y equals y, then 0, y, but then this one will be y plus height, same as this one, y plus height, then y, and then y plus height. Alright, so we got this create rectangle function. So where I had placeholder before, I had it somewhere, here it is. I can just do sprite.createArray, and so that'll create 2 triangles with all the values set as default. So 0, 0, it'll start at origin position 0, 0 and have a width and a height of 1. So it'll create a nice little square for us. But that's good for the geometry. Now we need to do the same thing for the texture positions. So basically almost near enough the exact same information, just at least for the moment anyway, just to get something rendered on screen. So we create a new texture buffer, and we assign it to as a buffer array, and we create pretty much the same thing. I'll illustrate this later once we got something going about how we can change these values and get different results, but for the moment it's good to know that it's just enough to know that we're creating some geometry using a square of width and height of 1 with an origin position of 0. Now that we have our mesh and texture information, we just need to assign them to variables within inside our shader. To do this, we have to find out the location of those variables, and we do this using getAttribute and getUniform. So we get the A position from our vertex shader and the texture coordinates. We also want to get our image, which is uImage. If we go back to our shader, we can see that's what we named it, uImage. But one thing to bear in mind, where these were attributes, our uImage is a uniform. So we're going to have to slightly change this. So instead of, let's change this first. uImage location. Instead of doing getAttribute location, we're going to go getUniform location. So pretty much very similar. Just all we have to do is change the word attrib to uniform. And that should give us the memory address of where our image is kept. And then, because we've been using this program the entire time, now that we got everything, we can set useProgram back to null. And we set this is loaded default to true. Sorry, whoopsie. So that means we've loaded an image. We've got we've signed a couple of rectangles to represent the sprite when it goes to render. We have the locations of its A position, its texture coordinates, and its image location. And we've pushed in a couple of. We created a buffer to store these rectangles representing the sprites. So I think we're pretty much Assuming there's no errors. Oh, there's errors. On line 90. Where it says this.program, should say this.material.program. Easy mistake to make. So, no errors, that's good. Okay, now we just need to write a render function. And our render function, let's keep it simple. So if this dot is loaded, which is referenced to this variable here, we wanted to do something. We wanted to render. So we have this here creating our new sprite. And then we have this update function. And let's just get this update function. In addition to doing this basic setup, we also wanted to do this dot sprite dot render, which will render our sprite for us. And hopefully, all being well, this will actually work. But before we move on, let's get rid of some of this black. Let's give it a nice, let's see, this.gl.clear color. So this is going to set just what color it is. So this is the red value, 0.4, so about 40% red, about 60% green, 100% blue, and 0% alpha. And this should be nice cornflower blue. Oh, that hasn't quite worked. Why is that not worked? Clear color, the color buffer, there's a typo there. So hopefully, yes, there it is. Oh, and also a typo here, or should say this dot sprite dot render instead of var dot sprite, and then we add in the line here, this dot sprite dot render. So we create a new sprite here in our game constructor, and then in our update function we tell that sprite to render. At the moment our render function is blank, so it shouldn't do anything, but the important thing is it's not throwing any errors either. So if the sprite is loaded, we really wanted to start rendering something. So let's get started into our render function within our sprite. So let's first of all, we'll get our GL set up. Let GL equal this.gl, just for convenience. GL.use program, and then we want to use the program associated with the sprite. This.material.program. And at the end, we also wanted to stop using this program, so we do this or use program null. So one of the things we wanted to do is do gl.draw arrays. This will actually draw our shapes for us. In our case, we wanted to draw a rectangle made out of two triangles. So it's a triangle strip starting at 0, and since there are 6 points, as I mentioned before, inside of our float array, then there are going to be 6 points pushed into our array. So this should do nothing yet. In fact, it should cause an error. There's no texture bound to units here. So we need to do a little bit of setup first. So the first thing we want to set up is our texture. So we do active texture. It's going to set up the whatever texture slot it is we want to use. So texture slot 0, like this. Ooh, no. Then we want to bind a texture, and it's going to be, the texture we want to bind is going to be texture 2D, and it's this.gl texture, the GL texture that we created when we first set up this sprite object. And then we want to set uniform 1i to this dot u image locale 0. So we're setting that value to 0. And we run that. Still nothing working. And the reason why that's not working yet is because we haven't set up our two buffers. Let's do that now. So first of all, let's set up our bind buffer, our texture buffer, gl.array buffer, and this dot text buffer. So that's a direct reference back up to here whenever we first created our texture buffer when we first set up this object. Then we need to enable, oh, is that it? No, it's not. Enable vertex attrib array. This dot a texture blah 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 blah. which again is a reference to this location we get up during setup. So we need to enable that, and we go vertex attrib pointer. We put in our a text location again. 2 triangles with precision float. Some value false, some value 0, some value 0. I don't know why we put those in there. I'm sure some expert could tell you. But this still shouldn't run. Oh, although it shouldn't throw an error. Where is the error coming from? Line 1010. So it was this function here. It doesn't like. Is there a typo in it? Yes, it should say pointer and not point. Okay, that seems to be going along fine. So that's putting in our texture buffer. So let's do the same thing with our geo buffer. And we need to use the A position like this, which I think is all pretty much the same values. And then let's see how that looks. Oh, we got a black square. Black square is an improvement, but it's not what we want. We wanted to show our image, and the image that we loaded in was this little fella with a pot. So what's gone wrong? Let's find out. What's this say? Bound to unit is not readable. It may be non-power of 2. Well, it's not. It's 256 by 256. Not that it should be an issue here anyway. And have compatible texture filtering. Oh, something's wrong with the texture filtering. Mirrored repeat. It said so magnified and minified are. So whenever texture. Aha! There we go. We've got our little fella in. Now he's upside down. There's a lot more complexity behind what's going on with the way it's rendered here. To sum it up quickly, without getting into too much, and to wrap up this particular episode, what I'll say is a WebGL or OpenGL window goes from -1 to +1, and -1 to +1, meaning that the center of the window is the origin point, which is 0, 0. So we got our triangles to render at 0, 0, as you saw earlier. We put in a default value of x of 0. So our origin point is 0, 0. And it went from 0 to 1 in width, 0 to 1 in height. So 0 to 1 in width is out this way, and 0 to 1 in height is up that way. And our coordinates for the image texture itself followed pretty much the same way. So rather than going, up the image, it went down the image, and it came up upside down and sort of over to the right here, where it's kind of off center. But that's what I promised to do today, was get an image displaying on screen. I didn't say it was going to be the right way up, but that'll do for our first tutorial. Now, I know that was a lot to absorb, and there was a few corrections going on and a lot of high concept stuff. But the important thing is here is that now that we have something displayed, getting a second one is really only a case of creating another sprite 1 and sprite 2, and let's get a second image. Let's see, this little happy fella will do. His name is NPC Smith. So sprite 2 NPC Smith, and whenever we render sprite 1, we also want to render sprite 2. And so now we have 2 sprites displaying on screen. So now you can get an arbitrary number of sprites displaying. Well, that'll give you the basics of being able to develop further and develop something that can move and something that can animate. And we'll work on that in the next episode. Well, thanks for joining me for this one. I'm sure that was as clear as mud, but I hope that you still found it very useful. And I'll see you on the next tutorial. Thanks very much, and you have a good day now. Bye!